I'm really delighted to introduce today's lecturer, Bryna Kra. We first met as graduate students in Stanford, so it's a special treat for me to have her here and to honor her for her awesome work. Bryna, who's now a professor at Northwestern University, has been selected for the 2019 Noether Lecture for her profound impact on mathematics, both through her work in the fields of dynamical systems and ergodic theory and through her service to the profession. Bryna is best known for her fundamental contributions to ergodic theory. Her joint paper in the Annals, Non-Conventional Ergodic Averages and Nil Manifolds, settled a long-standing open problem on the existence of the limit of certain multiple ergodic averages, uncovering the role of nilpotent groups in their homogeneous spaces and analyzing configurations in sets of integers. Her work continues to inspire a lot of other work and has had a great impact on ergodic theory. More recently, Bryna has been working in topological and symbolic dynamics, studying systems of low complexity, so systems with zero entropy, and that's what we're going to hear about today. In addition to her research, Bryna has been very inspirational to a lot of people, in particular young women, and she's started the GROW conferences, which encourage undergraduate women to go on to graduate school in mathematics. So thank you for being here, and join me in welcoming Bryna Kra.
So thank you very much for that warm welcome. It's really a pleasure to be here and to give this lecture. So Noether is a formidable figure. And sometimes we forget that what she had to endure, some of the things that, for example, when she started lecturing in Göttingen, and I think it was 1915, she wasn't lecturing under her own name. It was under her courses were advertised under Hilbert's name, with her as an assistant. And, now, in spite of her many achievements, she was never promoted to full professor there. But, of course, times have changed. Just look around this room. There's lots of women here. But I would say things haven't really completely changed. When I started as a grad student at Stanford and met Amy, there was a senior faculty member who asked me why I was pursuing my PhD and not my MRS. It took me a while to compute that one at the time. And I would say that probably every woman in this room who spent any time in a math department has also probably been confused for a staff person at some point. So while times have changed, and we've recognized Noether for her great achievements, there's a crater on the moon named after her, after all, I would encourage everyone in this room to think about what else we can do to further the conversation and continue thinking about change. So not just supporting greats like Noether, but supporting all mathematicians. And so I hope you take that as a conversation with you. So without further ado, let me turn to the topic of what I want to talk about. And I really want to point out that I would not be here, standing here lecturing to you, without my wonderful colleagues, many of whom are here in this room, and many of whom I will be talking about joint work with them, especially Van Seer, who is here somewhere, I believe. Of course, I can't really see any of you. And other joint work with also John Franks and Samuel Petit. So, what's my setting? I'm going to give you a very simple example, which is very difficult to understand. But the example is the circle. We'll think of it as the unit interval, 0, 1. And the map is the doubling map, so it maps every x to 2x, and you take it mod 1. So, I'm a dynamicist. I study orbits. If you look at the orbit of a point, you fix some x, and you look at x, 2x, 4x, and so on. Well, what can happen? Those orbits might be finite. If you start with a rational point, you'll end up with just a finite list of numbers there. It might be infinite. Some of them might be dense. They might be equidistributed, might have neither. So lots of different behaviors are expressed in this. And I want to contrast that system with a very different one, which is an irrational rotation. Again, same unit interval, 0, 1. And now I fix an irrational number alpha, and I take each x and I map it to x plus alpha. So it goes x plus alpha, x plus 2 alpha, x plus 3 alpha, and so on. And here the orbit is equidistributed. It fills up every interval evenly in some sense. And one of the questions I want to be talking about is how do you capture these different behaviors? It's one of the goals of dynamics. And so one of the tools that we have to do that is to code these systems. And this is the world of symbolic dynamics, which is what I'll focus on today. And so what I will do is I'll fix a point, and then I will code it by where its orbit lands. So if the nth iterate lands in the first half, I'll code it by a 0. And if it lands in the second half, I'll code it by a 1. Now, you'll probably agree with me, I'm cheating a little bit. There's a problem with 1/2, and 0 and 1 are identified, but let's just ignore that. It's a very small set on which there's errors. Okay, and so just for the sake of making things simple, I won't worry about those things. They can easily be dealt with. So let's look at the doubling map. And what happens when I start coding it? Well, let's say I pick this x here, which is in the first half, the left-hand side, and I start doubling it, 2x, 4x, 8x, 16x, and so on. I'll get some list of zeros and ones that come out as a sequence. And looking at this doubling map, what can I see in those sequences? Well, it's nothing more than the base 2 expansion of the number x. And if you vary x, you get the same behavior that I said happens in the orbits of the system, meaning you might get periodic, i.e. a finite sequence. You might have very few patterns. That's a case of low complexity. Or you might get all patterns, and that's the equidistribution type. On the other hand, if I do the exact same exercise with the rotation by alpha, I get a much more restricted sequence of zeros and ones that comes out by looking at alpha, 2 alpha, 3 alpha, all translated by the original x. And this sequence, if I look at it, it turns out, well, what's going on in it, there are very few patterns of zeros and ones can arise. So whatever length you look at, the number of patterns that I might see is highly restricted. And it doesn't depend on which x I started with. So it's not this list of possible behaviors. It turns out in the associated binary sequence, the frequencies of the zeros and ones, it's independent of whichever x I picked, so long as I fix the same rotation that I'm using at all times. So these are two very opposite things of the case of symbolic dynamics. So now let me give you some formal definitions. Moving away from the examples for a moment, we'll come back to both of those examples. So throughout this talk, I will fix a finite alphabet A. Usually it's going to be 0 and 1, and you can think of everything as just 0 and 1 for our purposes. And I'll endow it with the discrete topology. And then I'm going to look at bi-infinite sequences A to the Z, where all the entries come from that finite alphabet. Okay, and there's another area where you could ask for infinite alphabets or more general groups as my alphabets, but I'm just going to be sticking with finite alphabets. I put a metric on the bi-infinite sequences. It really doesn't matter which metric I use, but I just want to think, and I've written one down here, but I want to think about just a metric where two things are very close if they agree on a long central block. Okay, so in particular, if they're going to agree, they be close, they better agree at the 0th entry. And if they're going to agree, be very close for a long time, they better agree on the long interval around 0. So with this metric, it turns my space A to the Z into a compact metric space, and then I can endow it with the shift, which moves every entry over to the right. Or left. Yeah, left. Left shift. That will do. And one can check that the shift map is continuous, and so is its inverse map. And so what I've defined here is a dynamical system. And if you started and you saw the full alphabet, if my alphabet was K letters, let's say 0, 1, 2 up to K minus 1, then A to the Z with the shift sigma is called the full shift, meaning I'm allowing all patterns of 0, 1, 2 up to K minus 1 to show up anywhere, and I look at these patterns that arise. And otherwise I can consider restricted shifts, meaning I take some subset of the bi-infinite sequences, closed, invariant under the shift, and then if that X closed and shift invariant, then it's called a subshift. So it makes sense to look at iterations of the shift on this space itself. Okay? So that's what I mean, X comma sigma is a subshift in this setting. One of the very first things, if I give you a dynamical system or an object, you want to know what its symmetries are. So here are the symmetries. This is the automorphisms of this. It's any homeomorphism phi which commutes with the action of the shift. Okay, so it respects my dynamics on my space, so phi sigma is equal to sigma phi, and it's continuous, and I want its inverse to be continuous. And I will write aught of x for the group of all automorphisms. I really should write it as aught of x and sigma because it depends on the shift, but the same, I'm going to be using the left shift on everything, so I'll probably leave that out of my notation. So if you look at all such automorphisms, it forms a group under composition. You can compose two automorphisms and I still get another automorphism. And the first thing is, okay, you should notice that there's something in there, and that's all the powers of the shift are itself in this group. In fact, the powers of the shift are in the center of this group. Okay, so there is something there. And the questions I would like to ask is, what can we say about the automorphism group? And for example, here's a whole bunch of questions. Obviously, I won't answer all of these questions today, but you can ask, is this group abelian? Is it virtually abelian? Is it nilpotent? Is it amenable? And if you don't know what amenable is, you'll have a good idea by the end of this talk. What are its subgroups? What are its quotients? And one of the things I'm going to really focus on is the next few questions, which is, what are the relation between dynamical properties that I could put on my shift space and the automorphism group? Or what is the relation between invariance and complexity properties of the shift space and the automorphism group? Okay. Another question which I won't really have time to address, but will mention just in passing, is the automorphism group itself acts on the space, and you can ask what kinds of invariant measures. That's more towards the ergodic theory side of these things, but today I'm going to focus on symbolic. So let me give you a definition of what it means for a map to be a sliding block code. Okay, so, there's a formal definition here written down which says you're a sliding block code if you only depend on some central block, some window. And so maybe it's just best illustrated by a picture. So this is a map from my space to itself. It could be from the full shift space, or it could be from some subset X. And it's a sliding block code if when I want to know what it does to some element X, what I have to do is look at some fixed size window. That's the R in this. And the window I made it symmetric, so it's length 2R plus 1. And I slide it back and forth to determine the entry. And it outputs something at the middle entry there based on these entries. So you slide it along to see what the output would be at entry. Here is the entry at -1, then the entry at 0, the entry at 1, or actually at I minus I, I minus 1, I, and I plus 1. Okay, so it slides along to see. So the word of radius R, this block of radius R, around the ith symbol will determine the ith symbol in my image. Okay. So why am I introducing this? Well, there's a very old theorem of Curtis, Hedlund, and Linden, which says that if you give me a shift, x sigma, and any element of this automorphism group is a sliding block code. So if you go look for a paper of Curtis, Hedlund, and Linden in the literature, you won't find one. It's in a paper of Hedlund attributed to joint work with Curtis and Linden, who worked at IDA, and Hedlund published these joint results. So what this is very simple result. It's a nice exercise to work out the proof. Once you know this, is that if you give me an automorphism, it's a sliding block code. Well, this has several immediate corollaries. It says to me that any automorphism depends on this parameter R, the size of the window. And so in particular, the automorphism group is a countable group. Okay, well, easy, right? They're countable. They should all be easy. Okay. There's another consequence, which is about the entropy and the growth rate of something, and I will explain that momentarily what that means. That will come up. But I'll come back to that in a moment. So I said it's a countable group, and so you might say, okay, it's got to be a pretty easy group. But in the same paper, Hedlund showed that if you look at the full shift, so all patterns are allowed, this automorphism group contains isomorphic copies of lots of different things. Every finite group, the direct sum of any countable collection of finite groups, the direct sum of countably many copies of Z, and the free group on any number of generators, finite number of generators, or countably many generators. Okay, so it is not such a tame group in the sense it's got lots of things in it. And this was generalized for a large class of shifts. This is not just a property of the full shifts. And in a paper from 1988 of Boyle, Lind, and Rudolph, this was generalized for a big class of shifts called the subshifts of finite type, which are subshifts where you give me a list of restricted things that cannot appear as words, finite list, and then everything else is allowed. So it's a very broad class. And for all of these, the automorphism group is quite complicated. There's many different things in it. It's not a finitely generated group. It's not amenable. Again, I will define that in a little bit. It has positive entropy. I will define that also in a minute. And there's still lots and lots of open questions in this case, which I will not address because this is going to be a talk about low complexity. So let me define what I mean by low complexity. Okay. So let me introduce a little bit of notation. L of n will denote all the words, all the blocks in my subshift, all the blocks of length n. And my language is all of the allowable blocks, the union of all the LNs for all n, and going from 1 to infinity. So it's all that if you place down a window anywhere in it of any size, you just look at all of the things that you can see anywhere in my subshift. So we'll introduce the complexity function, and all it does is count how many blocks of size n you get somewhere in my shift. Okay, by looking anywhere at this, you slide it all over for over all the elements of my shift, and P of n, or P sub x, because it does depend on the shift, counts the number of words of length m. So this is actually maybe the easiest way to define entropy in a dynamical system, at least for symbolic systems. It's a very easy way to define it because the exponential growth of this quantity P of n is exactly the topological entropy of my system. So what I do is I look at log of the number of words of length n, divide by n, and take the limit as n goes to infinity. And you have to show that there's some subadditivity there, and so Feketti's lemma implies that this limit actually exists. So positive entropy is when this grows exponentially, and I will be looking at when this grows sub-exponentially. So P of n grows less than that. So let's go back to our two examples. The first was the doubling map. And in this one, I told you we see lots of behavior. Orbits can have different patterns. You get every sequence of zeros and ones that comes out. We're really seeing the full shift in its symbolic coding. And in this one, the entropy is positive. It's actually log 2 if it's code with zeros and ones, and it's the maximum achievable. On the other hand, if I look at the irrational rotation, the entropy is 0. Okay? It's a nice exercise to compute what this entropy is, but you can see it from doing the complexity by checking that if you look at the number of words of length n, remember I told you there are very few, well it turns out there's exactly n plus 1 for all n in this coding of an irrational rotation. And this is the minimum possible so long as my system is actually infinite. This is the Morse-Hedlund theorem, which I will explain in a minute. So these two opposite cases are showing us very different behavior in terms of the complexity, and hopefully we'll see this very different behavior reflected in the automorphisms. So in very, very low complexity, okay, this is an old theorem of Morse and Hedlund from the 40s, which says that my system X is finite if and only if there is a window, there is some n of a window of size n such that the complexity is less than or equal to n. Okay, so wherever I place down that, there's only one of n choices that I can see. So there's two short facts I will tell you about the complexity function. One is, well, what's the complexity of window size 1? It's the size of my alphabet. If you're not seeing something in it, you may as well throw it out of your alphabet because you're not using it. So it makes sense to assume that the complexity P of 1 is equal to the size of my alphabet. Bigger than or equal to 1 is not very interesting if it's 1. Okay? And in general, this is a non-decreasing function. The complexity of n is less than or equal to the complexity of n plus 1, because if you give me a window of size n, there has to be a way to build a window of size n plus 1, and I already saw that pattern. And in fact, these two facts are the only things you need to prove the Morse-Hedlund theorem. Because assume my alphabet is size 2. Okay? Otherwise it's trivial and it's a very trivial system. The one direction, if x is finite, then there is such an n. Well, this is just immediate from the definitions. Conversely, if I assume that there is some n such that p of n is less than or equal to n, and p of 1 is bigger than or equal to 2, and it's a non-decreasing function, well, somewhere in between there's a window where p of I is equal to p of I plus 1. Meaning I didn't gain any complexity when I looked at that window size. And what does that mean? It tells me that if I look at a window of size I, there's a unique way to complete it to a window of size I plus 1. So I move over, I have a new window of size I, there's a unique way to complete it. And I can keep sliding forward and backwards, and that window of size I determined the entire doubly infinite sequence. So what that says is, well, some point, there's only finitely many windows of size I, somebody's going to repeat. And so you must be periodic, moving along that way. So these are the two facts that prove the Morse-Hedlund theorem. So in this setting of very, very low complexity, the space X is just periodic points, the automorphism group is finite, and so I want to view this as a corollary that if you can embed Z into the automorphism group, then your complexity cannot be bounded. Because remember I told you the automorphism group always contains all the powers of the shift. Well, that's how I embed Z, but I need at least an infinite space to be able to do this. So from now on I will assume that P of n grows at least like n. P of n is bigger than n for all n. So I can embed Z in it, and my question is, what more can we say? Okay, so I'm going to now raise the complexity to linear. So I'm going to assume just linear growth, and I will assume for now that the lim sup of P of n over n is bounded less than some k. This includes the example of the coding of the rotation that we looked at already, where it was exactly P of n is equal to n plus 1. This class of shifts is called the Sturmian shifts. They were named so by Morse and Hedlund. And more generally, if I take any minimal shift with this complexity is measurably isomorphic to an irrational rotation. So the only reason I'm saying that is it's not just codings of rotations. There are many things which have linear complexity. And if you know, for the experts, if you know what these are, there are substitution systems such as the Tui-Morse system, codings, the natural coding of an interval exchange transformation, and various other transformations. So there's a class of shifts like this. So under this assumption of linear complexity, and this is a growth on the lim sup that I'm assuming here, it turns out that we have a strong restriction on the automorphism group. And the restriction is that every finitely generated subgroup of the automorphism group is virtually ZD for some D, where this depends only on the growth rate of the complexity, D less than K. So in contrast to this example of the full shift that I gave you, where we saw lots of things embedding into the automorphism group, what this tells us is that the question really changes. And the right question to ask for these low complexity ones is not what can you put in, but it's which do not embed. What kinds of groups do not embed into this automorphism group? So let me just copy up that theorem, the one that I stated, which says that if you have this complexity assumption, low complexity, every finitely generated subgroup is virtually ZD. Okay. And I would now like to put on this some more dynamical assumptions. So far I have not made any restrictions on the dynamics. It's a subshift, and that's it. Well, one of the restrictions I can say is to say that the dynamics are simpler in some sense. And a first notion of simpler in some sense is transitivity. And what that means is that there is some point x in my space such that the whole shift space is generated by that point. So there's some point x so that if you take its orbit closure under the shift, I see everything. Okay? Okay, so the full shift, for example, there you could make this as an orbit closure, but here we're in a very opposite setting of very low complexity. And it turns out then that I get even more restrictions on the automorphism group. If it's transitive, then the automorphism group is virtually Z as opposed to being virtually ZD. I can then strengthen my dynamical assumption on this by instead of insisting that there's just one point, I can say, how about if every point has this property? And this is exactly minimality. It means you pick out any point in my space, I take its orbit closure under shifting forward and backwards, and I see the whole space. So obviously minimality implies transitivity, but transitivity does not imply minimality. And in this case, we get the same result because it's a weaker, it's obviously transitive, but it turns out we can weaken the hypothesis to being, instead of a lim sup assumption on my complexity, a lim inf assumption. The last result was proved in the same time as we did in another paper of Donazeau, Duran, Mas, and Petit. So now let me, linear complexity is one in which we pretty much understand what's going on. In fact, we have examples that achieve all of these kinds of groups for the automorphism group. And what is being used in them is that this very strong restriction is that there are only a few words, depending on the complexity, that can be extended in more than one way. So this argument I gave you from Morse-Hedlund, there's something similar in flavor that works in linear complexity for extending to saying more about this. And there's some similar ideas that get used in this case, and it's the only case in which we can say these kinds of statements, to bound the number of ergodic invariant measures on my space. And the final comment I will make about this linear complexity is that all of these results are sharp in the sense that we really know examples of shifts where these automorphism groups are exactly virtually ZD or virtually Z or and so on for all of them. But linear complexity is unfortunately much simpler than raising the complexity even just a little bit. So now, keeping in mind this complexity function, I'm still talking about P of n counting the number of words of length n. I'm going to go up to quadratic growth now. And let me give you, okay, there's a complicated definition of what it means to be amenable, but you don't have to read it. Okay, it's the technical definition, but what does it mean for a group to be amenable? It means that there's a nice way of averaging on it. So think about Z. If I want to take an average over all of Z, I would take bigger and bigger intervals around 0 and use those to average from minus n to n, for example. The existence of such a sequence over which I can average, that's called a Fulner sequence, which is defined there, that's what it means for a group to be amenable. So all the nice groups on which I can do this averaging scheme are amenable. It's a sense in which a group is tame in some sense. And we would really like to be able to say that all the low complexity shifts have automorphism groups that are amenable. So in this direction, if we take a shift and its complexity grows sub-quadratically, so it's big O of n to the 2 minus epsilon for some epsilon, then the automorphism group has this nice property, it is amenable. So it's much tamer in some sense, and again, I want to contrast this with the full shift, where we did not have this property at all for this many classes with things with positive entropy. And in fact, we can say stronger statements if we put some dynamical assumptions. So again, this transitivity assumption, if I ask that there exists a point whose orbit is dense in the shift, then I can, if I have this lim inf assumption of lim inf of the complexity over n squared is 0, then I actually get, once I modify out by the shift, which must be in there, and at all its powers, I get a periodic group. Okay, so every element has finite order. And in fact, with minimal, I can say even more that every finitely generated torsion-free subgroup is virtually abelian. And already we begin to see that in the quadratic case, there's a big difference between what I can say for general shift and what I can say when I make very strong dynamical assumptions like minimality and transitivity. But the results that we get out are already weaker than the linear case. Okay. So you might say, what's special about quadratic? Let's raise the complexity up to any polynomial, for example. And so, the first result is, or maybe actually our only result in the polynomial case is the following. Again, all of these results are joint with Van Seer. If I take a minimal shift, to remind you what that means, every orbit is dense. Okay? Take any point and you take its orbit closure, I see the whole thing. And it grows, with a lim sup condition on the complexity like the polynomial n to the d. So P of n, over n to the d, the lim sup of this, it tends to 0. for some D. Then I get tameness of my automorphism group in the sense that they're all amenable. Okay, so there is some way to average in them. But we can say a lot more here, that if you take a finitely generated torsion-free subgroup of the automorphism group, it's virtually nilpotent. Okay, so it's much stronger statement than just saying that it's amenable. Okay. And there's a bound on the step of the nilpotent group. And what I want to think of this as saying is that you cannot embed ZD into my automorphism group if this shift grows too slowly. Okay, for a minimal shift. I cannot embed ZD if P of n is little o of n to the d. There's no room for it in there. Okay? And in fact, what this says is if P of n is little o of n to the fourth, if you do the computation with the step with one step nilpotent is abelian, then every finitely generated torsion-free subgroup is virtually abelian. And in a more recent paper with Cyr, Franks, and Petit, we managed to improve this same statement to little o of n to the fifth. Okay, 1 degree more, and we still get virtually abelian. And I hope you're getting this idea that there's lots of questions here, because it's not clear that little o of n to the fifth is anything other than an artifact of our proof. Okay. All right. So, polynomial growth, that's nice, but how about raising the complexity and still staying within the zero entropy regime? Okay, so the next one is to go to stretched exponential growth. Again, I'm assuming minimality. My shift is minimal, meaning every orbit is dense. And now I have a growth condition that log of P of n over n to the beta tends to 0 for some beta that's strictly between less than a half. Okay, 0 less than or equal to beta less than a half. And once again, I get that the automorphism group is tame in this sense. It's amenable. And every finitely generated torsion-free subgroup here has sub-exponential growth. So let me explain what that means. When I'm looking at the growth function, what that's doing is counting the number of group elements that can be written as a product of at most n generators, where I take the generators from a symmetric set of generators. Okay, a priori, the way I write that depends on my choice of the generators, but the growth rate of this does not depend on the of the generators. Okay, so this is what I mean by any finitely generated torsion-free subgroup has sub-exponential growth. Okay, so I hope you see that there's a few questions hiding in this theorem. Right? There's a stretched exponential and it only goes up to beta less than a half. And I've also made some strong dynamical assumptions on this. And there's another hidden question that I'll leave for a little later, which maybe you see in this. But let me now raise the complexity all the way up to anything with zero entropy. Okay, because that was really the goal of our project, is to really understand the automorphism groups of any of these low complexity shifts. So let me introduce one more definition. If I take a group and I write an element as L of G denoting the shortest presentation of it. So the way to write it in a symmetric set of generators with the fewest number of generators, then this element G is said to be exponentially distorted if the way of writing its iterates, L of G to the n, is short. So it's big O of log n. Okay? Again, L of G, the actual way to write it, depends on which generators, symmetric set of generators you choose. But being distorted or not is not dependent on those generators. You either are exponentially or not. And so there are groups with exponentially distorted elements, ones that you know, like SL3Z or SLKZ for any k bigger than or equal to 3. The Baumschlag-Solitar group, BS1N, which is the group with generators A and B such that BA, B inverse is equal to A to the M. Okay, so those have exponentially distorted elements. And remember our question is, in low complexity, which groups do not embed? Okay? And these are exactly examples of groups that do not embed in zero entropy shifts. So if we take a zero entropy shift, so this is sub-exponential growth of this complexity function, then you cannot have a finitely generated subgroup of the automorphism group with exponentially distorted elements. In other words, I can't have subgroups that look like Baum-Slug-Solitar 1n or SL3Z. And this was actually the first example of a finitely generated group that does not embed into any zero entropy shift. Okay. In fact, we do not know if these exact groups, SL3Z or BS1N, embed in the full shift. We have now just eliminated them from embedding in the zero entropy shift. Okay. And this answered a question that was in a paper of Donozo, Durand, Petit, and Mas. So, this is everything I told you. Now, let me tell you how to read this chart. Okay? On the top line, on the left-hand side of this chart, is a complexity assumption. And for each of these theorems, they all have the same format. You take the complexity, you throw in some dynamical assumption in addition, and you get out something in the automorphism group. You can say something about the automorphism group. So there's two ingredients, bounds on the complexity, something about the dynamics, and I want to say something about the associated automorphism group. So as an example, the very first line says, okay, strictly speaking, it's not quite just positive entropy, but allow me to tell a slight lie for this purpose. It says if you have such a shift, for example, the full shift, well, the automorphism group is pretty darn complicated. Okay, it's got lots and lots and lots of behavior in it. I showed you lots of subgroups that embed in it. The strongest result we were able to say about zero entropy, arbitrary shifts with zero entropy, is on the second line. And that says that you don't need any dynamical assumption. And what you get out is that you can't have subgroups or elements with exponential distortion living inside this. And so on. It continues down. In fact, there's some other results here which I didn't mention, some other results about what happens in various things. For example, down at the quadratic level, there's some stronger results than the ones that I stated. But I want to contrast this, and I hope you can see the colors, of now everything on this same slide that's green is an open question. Okay? So I'd like to go through this and tell you some of the many open questions that remain in this. So on this first line, let's say I'm looking at the full shift. Okay, so the full shift, remember, I would take two symbols, for example. I allow all patterns. This old theorem in Headland's paper, it says that this contains lots and lots of different things, and since then there have been other papers that have shown it also contains other patterns. Well, what if you took the full shift on two symbols and the full shift on three symbols? Okay? They each have an automorphism group, and we do not know if they're isomorphic. So even the most basic questions on the full shifts are still open. To make matters worse, we do know that if you take any subgroup of the full shift on two symbols, it embeds into the full shift, the automorphism group of the full shift on three symbols, and vice versa. So this is a pretty subtle question whether or not these are isomorphic. Okay. So that's the first line that we're looking at. There are many other questions. This SL3Z, which I told you it's hidden in there on the second line, does not embed into the automorphism group of a subshift with zero entropy. We don't know if it embeds into the full shift, or more generally any one of these mixing subshifts of finite type. Okay, same with Baum-Slug-Solitar 1n. We don't know if it embeds. There are very few restrictions that can be placed on such, very few non-trivial restrictions that we know about for that automorphism group. So if we move to the second line now with zero entropy, okay, well, without any assumption on the dynamics, there's really not much I can say. I can say there's no exponential distortion, which was the result that I told you, but that doesn't tell me if there are elements with group distortion, which is a weaker notion. For example, could I embed a two-step nilpotent group, the Heisenberg, the discrete Heisenberg in there? This is completely unknown whether it be zero entropy or positive entropy. So I don't know if I actually have distortion embedding into this. Okay, not the exponential type of distortion I was talking about. When we reduce the entropy, reduce the complexity rather, and we're in this case of the stretched exponential where beta is less than a half, strictly less than a half, my assumption, which is also in green there, was that the lim sup of the log of p of n over n to the beta was 0. Well, that's an open question whether or not that's the right assumption or if it's lim inf. We don't know. Okay, so that's why that one's in green. The next assumption I had on there was that it's minimal. We don't know if that dynamical assumption is necessary to conclude that the automorphism group is amenable. Right, because that line reads as, with this stretched exponential beta less than half assumption and minimality of the shift, my automorphism group is amenable. And perhaps the most disturbing part of that line is the last column, which says, what is an example? And in fact, we do not have any example of such an automorphism group that is not virtually abelian. Okay, so the example column is a very unfortunate defect that we have a dearth of examples in this area. Okay, so when we know that the automorphism group is amenable, it's restricted, it's simpler in some way, tame in some way, we do not know if that's the right answer and the right theorem that we should be getting out there in this last column. The same question continues when I have growth rate of little o of n to the d for some d bigger than 1. If I make the assumption that my system is minimal, then I know that any finally generated subgroup is virtually nilpotent, but hidden inside this again is that same pesky question. Are they virtually nilpotent or are they actually virtually abelian? Okay, and so we don't know the answer to that. Again, reducing the complexity to getting down to little o of n to the fifth with minimality, we do know that that one is sharp. It's virtually abelian. And we can produce an example that is that. But it may be that those two lines are the same. And so by this, I mean the line of n to the fifth and n to the d should give out the same answer, not virtually nilpotent, but virtually abelian. We don't know. When we get down to the subquadratic case, so here it's listed as little o of n squared over log squared of n. This one has no dynamical assumption, and we're able to show that it's amenable, but once again, we don't know if that's really the correct answer, and maybe it's a much simpler, if we had some examples. And even, so I said to you earlier that, continuing in the polynomial case, we still have this question about the correct assumption being the lim sup or the lim inf, and that's this line right here. It's on this side, whether that's the correct assumption. And even in the linear case, which I told you we completely understand, well, I have to be honest that we don't know if lim sup is the correct assumption or if it really should be instead lim inf for all of this. So these automorphism groups, there's a lot that we can say about them, but I hope I've convinced you that this is a very active area with lots of questions and a very different type of question for high complexity, meaning positive entropy, and low complexity. For one, you're trying to push as many things as possible into the automorphism group and show that it is not constrained other than by some simple constraints that it must happen. Or on the other side, trying to show that it really is a very much simpler, tamer type of group where you can't see these things. Thank you. That means it has whichever group as a finite index subgroup. Okay, so virtually abelian means it has an abelian group as finite index.
Any other question?
So sorry, I missed this. What does it say about the doubling map?
Okay, so the doubling map is up in this very first line with the high complexity. Its coding looks like the full shift. And so its automorphism group contained many different things. You can embed, for example, the free group into the automorphism group. Okay, so it's a complicated automorphism group.
So, I missed this point. So why is a homomorphism important for the looking at distribution?
You mean on the shift? Well, so the systems, I'm considering it as the system and the automorphisms of the full system. So I want to give you the map with the space to look at the two and study the automorphisms of the dynamical system rather than just of the space X. Right? So I'm respecting the dynamics that come with the shift at all times. So it always commutes with the shift.
Can I ask this very simple question? You talked about the full shift on 2 symbols and the full shift on 3 symbols. You said the automorphism groups are unknown somehow, or unknown whether they're the same. And then you said subgroups of the first, embedded the second. That's obvious, and vice versa.
Oh, it's not obvious.
Well, you meant, I thought you meant it was fairly obvious, but then you said vice versa. What's that?
So subgroups of the full 3 shift, the automorphism group of the full 3 shift, embed into the full 2 shift. Subgroups into the automorphism group of the full 2 shift. And 2 and 3, there were any 2 numbers. Could have been 10 and 12. We don't know that any of them are isomorphic or any pair are not. Well, that's not true. We do know that 2 and 4, okay, when one of them is a square, it is not isomorphic. Its automorphism group is not isomorphic to. And this one is follows from a very beautiful theorem. It's called Ryan's theorem, which says that the center of the automorphism group is just powers of the shift for the full shifts. And from that one can see that one of them has a square root and the other one doesn't. And so this distinguishes the automorphism group on 2 and 4 symbols. But 4 and 6 symbols? No, 4 and 6 I can distinguish. 4 and 12, yeah. Now I'm in trouble.
One more question. One quick one.
So, you look at others, here we have some listed growth rates, and others,
Sorry, I couldn't hear.
other growth rates. You have other,
Oh, other growth rates, you mean,
you have some list here, but there's other things in between some of these.
right. So, here I've just focused on, well, I've covered everything up to 0 entropy as either polynomial or superpolynomial and sub-exponential. But you could ask for a very specific growth rate. And one can construct shifts that achieve many growth rates. You can construct shifts that are arbitrarily high growth rates and still being sub-exponential. There are classes of shifts that do this. But there's a lot of questions about which growth rates exactly, how to exactly, not just the rates you can achieve, but particular growth functions. There are many questions.
What about non-symbolic systems?
The question was, what about non-symbolic systems? We're so stuck on so many symbolic ones where we have so much more to work with. Well, there are lots of things one can say about more general automorphism groups and topological settings, but we're not there yet.
Okay, so I want to thank you all for your questions. Thank you very much, Bryna, for the excellent talk. And I want to I want to present you with this plaque from the AWM and the AMS to honor your 2019 Noether lecture. So thank you.